in the previous lecture we had discussed that what is meant by statistical testing and what is the concept of statistical null hypothesis and statistical alternate hypothesis, and how these are used in sorting out the biological problems and how they are linked to the statistical analysis or statistical testing. And then we also saw the definition of one-tailed and two-tailed test. So from now onwards, we are going to start the statistical tests that make use of the statistical null hypothesis and alternate hypothesis, and we will see that how these tests they are executed, that how we formulate our null hypothesis, how we formulate our alternate hypothesis, and how do we do these calculations. So we will do the simple statistical tests, the basic statistical tests, and we will start from those tests which involve the analysis of frequencies. For example, if you have your data or if you have your observations in a form which are the frequencies of your variable, which are the counts or frequencies of your variable in different categories or in different classes. So how you can analyze your data. So the simple test that we can use for the analysis of frequencies is the chi-square test. So in chi-square test, the observed frequencies are compared with expected frequencies on the basis of some null hypothesis. So in this case, you have your observed frequencies that you have taken after your sampling or after your experiments. So these observed frequencies, they are compared with the expected frequencies on the basis of some null hypothesis. It means that you are going to compare your observed frequencies with some expected frequencies on the basis of some model which you built according to your null hypothesis of the experiment. So this is a simple calculation, and this is not the letter X, this is the Greek letter chi. O means observed frequencies and E refers to the expected frequencies. So this is the simple formula of the chi-square test, and there are different forms of the chi-square test that make use of the same formula, but their null hypotheses are different. And the three basic types of the chi-square test, they include the chi-square test of homogeneity, goodness of fit chi-square test, and the chi-square test of independence. So general procedure in any kind of the chi-square test is that first of all, whenever you have your samples or whenever you have your observations, you have to choose the type of chi-square test on the basis of your experiment, that what kind of experiment are you doing, what is your experimental hypothesis, right? So you have to choose the type of chi-square test that you're going to use. And then you have to state the statistical null hypothesis and alternate hypothesis for your statistical test. And then you have to calculate the expected frequencies on the basis of null hypothesis, because you already have your observed frequencies on the basis of the experiment, on the basis of sampling that you did. So now you have to calculate the expected frequencies under the null hypothesis that you have proposed. And then do the calculations, do these calculations and calculate the value of chi-square, which is your test statistic. So what is the next step when you do the test statistic? So when you have your test statistic, what do you do with that? We discussed in the previous lecture. So when you have your test statistic, when you have your calculated value, you compare it with the tabled value of that specific test. So now you have to compare test statistic, which is the calculated value of chi-square, with the tabled value from the chi distribution table. And after you have done this comparison, you're going to state your results, that whether your results are significant or your results are not significant. So this is the general procedure for any kind of the chi-square test that you're going to use. Now, starting from the chi-square test of homogeneity, this is the simplest type of the chi-square test, and it is the test for homogeneous frequencies. So in this test, the assumption is that the frequency distribution is uniform in all classes or categories. So all of the classes or categories that you have, the frequency distribution of your variable is uniform in all of those classes. It should be homogeneous, that there should be no difference, there should be no significant difference in frequency distribution of your variable among different categories or among different classes. So this is the basic assumption of the chi-square test of homogeneity, which is the test for homogeneous frequencies. And we are going to take the example of Dixella insects. So a biologist collects a sample of Dixella pupae from a pond, and these pupae, they are morphologically indistinct. They are morphologically similar to each other, and they emerge out in following numbers: Dixella autumnalis, Dixella aestivalis, Dixella amphibia, and Dixella attica. So these are the 4 species of the Dixella that are present in that community, that are present in that pond, and they emerge out in these numbers: Dixella autumnalis 24, Dixella aestivalis 32 out of the 75 pupae, Dixella amphibia 10 out of 75 pupae, and Dixella attica 9 out of 75 pupae. So this is their frequency distribution. So these species, they are the classes, they are the nominal categories, and these are their frequencies, which are the number of pupae belonging to respective species. So this is the kind of distribution that you get. So unless and until you have some previous observation or previous finding that what is the species composition in that community or what is their relative distribution, so unless and until you have that, you have to assume that these are homogeneously distributed, that their distribution should be homogeneous. So apparently we can see that these are not homogeneous. So out of 75, Dixella attica is only 9 and Dixella aestivalis is 32. So apparently we see that there is a difference between their frequencies. So now we want to confirm that whether this difference is a significant difference or this difference is not a significant difference. So for that purpose, we are going to use the chi-square test of homogeneity. So question is the distribution of frequencies between the categories homogeneous? So this is our question. And we are going to use the chi-square test of homogeneity. So what is the next step? The next step, after stating the problem and after choosing the type of the chi-square test that we are going to use, we have to state the alternate and null and alternate hypotheses. So our null hypothesis is the observed frequencies are homogeneous and the departure is merely due to the sampling error or scatter. So this is our null hypothesis, in which we are assuming that this difference is non-significant and this difference is only because of some sampling error or scatter. And then the alternate hypothesis is the observed frequencies depart from those expected of a homogeneous distribution by an amount that cannot be explained by sampling error alone. So in the alternate hypothesis, we're assuming that this difference is significant, and this difference is significant enough not to be accounted only by the sampling error. So these are our null hypothesis and the alternate hypothesis. So what is the next step after we have stated our null and alternate hypothesis? The next step is calculation of expected frequency on the basis of the null hypothesis that we have stated. So our null hypothesis was that the frequency distribution in all of these classes is homogeneous. So if our null hypothesis is true, we expect that 75 pupae should be distributed homogeneously between the 4 nominal categories. And for that purpose, we will do the calculation, which is how many categories or classes do we have? We have 4 classes. So 1 by 4 into 75, which is the total number of observations. So 75 divided by 4 is 18.75. So 18.75 number of pupae should be present in every category. And this is the table for the calculation of chi-square value, and the chi-square value can be calculated by using this kind of a simple table. And in this table you can see that there are different columns. So the first column refers to the column in which we have stated our classes or our categories, and in this case these categories are the names of the species of these insects. So in the second column we have the observed frequencies that we have observed, and in the third column we have the expected frequencies, and as you can see that the total of the observed and expected frequencies, that should be same. And then in the next column we have the difference of observed and expected frequencies, which is O minus E. And then in the next column we have the square of this difference between observed and expected frequencies, and in the last column we have this square of the difference divided by the expected frequencies. So as you can see that we have to do this calculation separately for every class, and then we take the sum of the last column, and that sum is actually our chi-square value. So this is the method of calculating the chi-square value from your observed and expected frequencies. Now the calculations, the observed frequencies and the expected frequencies. Then we have the difference of observed and expected frequencies. So 24 minus 18.75, which is 5.25, 32 minus 18.75, which is 13.25, and then 10 minus 18.75 minus 8.75, 9 minus 18.75, which is minus 9.75. So you have to ignore this minus sign in the last two rows. Why? Because we are going to take square of these values in the next column, so it's not going to make any difference if there is a minus sign or if there is a plus sign with your values. So we are going to take the square of these individual values. So square of 5.25, which was the difference of observed and expected frequency of Dixella autumnalis. Then the square of 13.25, which was the difference between observed and expected frequency of Dixella aestivalis. And then the square of 8.75, which was the square of difference between the expected and observed frequencies of Dixella amphibia. And then the square of 9.75, which is the difference between observed and expected frequency of Dixella erica. And then we have our last column, in which we divide this square of the difference between observed and expected frequencies by the expected frequency. So we have this 27.5625, and why I'm taking this long number is because when we round off during the initial stages of calculations or during these intermediate steps of calculations, we are going to end up with a different number and we are going to have a different result. So we have to take at least 4 digits after a decimal so that we have the precise calculation at the end. So 27.5625 divided by the expected frequency, and the result is 1.47. So we calculate that for every class. For Dixella aestivalis, the square of the difference divided by the expected frequencies is 9.3633. For Dixella amphibia, it is 4.0833, and for Dixella erica, it is 5.07. And now we have to take the sum of these values, 1.47 plus 9.3633 plus 4.0833 plus 5.07, and our sum is 19.987. So this is the value of our chi-square. This is our calculated value. Now our calculated value is 19.987. So what should be the next step? Next step is to see what is the degree of freedom, which is n-1. N is the number of classes, -1 is 3. So our next step is to see that what is the probability of a null hypothesis to be true, and for that purpose we have to compare our calculated value with the tabled value. And our null hypothesis is the observed frequencies are homogeneous and the departure is merely due to sampling error or scatter. So we are going to compare our calculated value with our table value to see that whether this null hypothesis is true. What is the probability of this null hypothesis to be true or no? So this is our chi-square distribution table, and in this table, as you can see, that we have the columns which represent the probability values for different levels of significance, and they are arranged in the rows according to the degree of freedom. So what was our degree of freedom in this case? It was 3. So what is our first level of significance? It is 0.05. and the value is 7.815. So what was our calculated value? Our calculated value was 19.987. So which one is greater, our calculated value or the table value? Obviously our calculated value is greater, 19.987. It means that we reject null hypothesis in favor of alternate hypothesis. And the significance level is 95%, which is said to be significant. Now we are also interested in seeing that what is our next significance level. That at this step we reject the null hypothesis. So null hypothesis stands rejected at this point. So in the further steps we are only going to see that what is our maximum significance level of these results. So what is our next level of critical probability or significance? It is 0.01, and what is the value there? It is 11.345. So this value is also less than the calculated value, therefore this result is also significant at 99% significance level. So this result is highly significant. And now we move on to our next level of critical probability of significance, which is 0.001. And here we can see that our calculated value is also greater than this value. This is 16.266, the table value at 0.001, significance level of 99.99%. So our results are very highly significant, that there is a 99.99% probability that our null hypothesis is false, right? So probability of a null hypothesis to be true is less than 0.001. Therefore we are rejecting a null hypothesis and we are accepting the alternate hypothesis. So what should be our results? This is our last step, the results. There is a statistically very highly significant departure from homogeneity between the four categories. Chi-square 19.987 and probability less than 0.001. Distribution of the four species is not homogeneous in the population. So this is another way to state our results, that we say that the distribution of the four species of Dixella is not homogeneous in the population, in the community, and stating the chi-square value and the probability of significance of these results. So this is how we do the chi-square test of homogeneity, and this is how we state our results. Our next type of the chi-square test is the chi-square goodness of fit test. So as its name indicates, that it is comparison of observed frequencies to an expected predetermined model or ratio. It means that we are not assuming them to be homogeneous, or we are not assuming them to be the same in all categories. Rather we are assuming that these frequencies, they should appear in a pattern, they should appear in a ratio. And we are going to check, we are going to test that whether our observed frequencies, they fit into that ratio or no. So what is the goodness of fit of our observed frequencies into those expected under that predefined ratio? And we are going to use the Mendelian ratios, for example, the law of independent assortment. So you remember that what is the phenotype ratio, what is the expected phenotype ratio? It is 9:3:1. So this is the phenotype ratio for the law of independent assortment. So a farmer did a dihybrid cross of pea plants, and the plants were heterozygous for two traits. So these two plants, they were heterozygous for two traits, and he did the dihybrid cross of these pea plants. And these two traits were seed appearance and color. So this is the very famous example that every biologist, every biology student, that they study during their courses. So this is a very basic example of genetics, and you all must be familiar with these examples. So that is why I have taken this example. This is the example of law of independent assortment. So this farmer obtained the progeny of 556 seeds. Out of these 556 seeds, 315 were round yellow, 108 were round green, 101 were wrinkled yellow, and 32 were wrinkled green. So these were his results. Now the question is does the result of this cross follow the Mendel's law of independent assortment? So this is the biological question, or this is the statistical problem that we have, that does the result of this cross follow the Mendel's law of independent assortment? The next step is to state the alternate hypothesis. Our null hypothesis. Our null hypothesis is the observed frequency distribution follows the Mendel's law of independent assortment. And our alternate hypothesis is the observed frequency deviates from the Mendel's law of independent assortment. So these are our hypotheses. The next step is calculation of expected frequency, and how we do calculate the expected frequency on the basis of our null hypothesis. So our null hypothesis is that this cross, the results of this cross, follow the Mendel's law of independent assortment. So therefore the phenotypic ratios should be 9, 3, 3, 1. So we calculate the expected frequencies on the basis of this model. So first of all, we calculate their ratios, we calculate their proportion values. So round yellow, 9 by 16. So what is the total of 9, 3, 3, 1? It is 16. So 9 by 16 is 0.5625. 3 by 16 is 0.1875. And 1 by 16 is 0.0625. And now we calculate the expected frequency. What is the total number of the progeny that the farmer had? These are 556. So 0.5625 out of the 556 should be the observed frequency for round yellow, which is 312.75. And for round green and wrinkled yellow, it is 104.25 each. And then for the wrinkled green, we have 34.75, and their total is 556. So this is how we calculate the expected frequency. So we are not considering them to be homogeneous, we are considering them to be following a predetermined ratio. And now the table for the calculation of the chi-square value. We have observed frequencies, we have expected frequencies, the total is same. So next step is the calculation of difference between observed and expected frequencies. The difference between the observed and expected frequency of round yellow seeds is 2.25. The difference between the observed and expected frequency of round green is 3.75. The difference between the observed and expected frequency of wrinkled yellow is 3.25, and the difference between the observed and expected frequency of wrinkled green is 2.75. And what is the next step? To take the square of these values, the difference between the observed and expected frequency of round yellow, the square of 2.25, and the square of 3.75, the difference between the observed and expected frequency of round green, then 3.25 square, the square of the difference between the observed and expected frequencies of wrinkled yellow, and then 2.75, which is the square of difference between the observed and expected frequencies of wrinkled green. Now we are going to divide this difference with the expected frequencies. So 5.0625, which is the square of the difference between observed and expected frequency of round yellow, is divided by the expected frequency of round yellow. And we have the value, which is 0.0162. So we do the same calculation for round green, for wrinkled yellow, and for wrinkled green. Now we take the sum of these individual values, 0.0162 plus 0.1349 plus 0.1013 plus 0.2176, and their sum is 0.47. So this is the value of the chi-square that we have. So what should be our next step? Next step is to define the degree of freedom and to compare this calculated value with the table value of chi-square. So our degree of freedom is, because there are 4 classes, so degree of freedom is 3. The table value that we took from the table of chi-square distribution is 7.815 at probability of 0.05. And as we can see that our calculated value is less than the table value at probability 0.05, so we are going to accept the null hypothesis. So the probability of null hypothesis to be true is greater than 0.05, therefore the results are non-significant. And therefore we are free to state that the result of cross follows the Mendel's law of independent assortment. The chi-square value is 0.47 and the probability of this value is greater than 0.05. So this is how we do the chi-square goodness of fit test. Then we have another example of the chi-square goodness of fit test, and this example is about the species composition of ground foraging birds, and 64% of the ground foraging birds in that area, they are sparrows, 29% are larks, and 7% are francolins. And these observations, they were made on the studies that were done in the past from that area. That 64% of the ground foraging birds are sparrows, 29% are larks, and 7% are francolins. So this is the frequency distribution that we have in that area. And then after 30 years, a new study was done to find out that if the species composition is same as previously found or has it changed over the period of time. So 750 birds were observed, and out of those 750 birds, 495 were sparrows, 198 were larks, and 57 were francolins. So this was the species distribution in the new observation. Now the question is there any change in species composition, or is the species composition same as previously found, or it has changed? So this is the question that we are going to check. So again, we are dealing with the frequencies, so we have to apply the chi-square test. And what kind of chi-square test? The chi-square goodness of fit test, because we have a pre-existing ratio, the pre-existing relative frequencies of different nominal categories. So the next step is to state the null and alternate hypothesis. Our null hypothesis is there is no change in species composition of the area and it is same as previously studied. And alternate hypothesis, obviously it assumes a difference and it says that species composition is different from previous study. So these are our hypotheses. Next step is calculation of expected frequency under our null hypothesis, and this is how we do it. So sparrows, according to the previous study, they were 64% of all ground foraging birds, larks were 29%, and francolins were 7%. So this is how we calculate their proportions. That 64% means 64 out of 100, which is 0.64, and then 29 out of 100, which is 0.29, and 7 out of 100, which is 0.07. And the expected frequency in the 750 birds that were observed, the expected frequency is 0.64 into 750, which is 480 for sparrows, and 217.5 for larks, and 52.5 for francolins. So these are our expected frequencies. Now we have to apply the test. This is our chi-square calculation table, the observed frequencies and the expected frequencies, and you can see that their sum is similar. Then the difference between the observed and expected frequencies, it is 15 for sparrows, 19.5 for the larks, and 4.5 for francolins. Again, you have to ignore the minus value because we are going to take the square of this difference in the next column. So 15 square, which is the square of difference between observed and expected frequencies of sparrows, 19.5 square, which is the square of difference between the observed and expected frequency of larks, and 8.75 square, which is the square of difference between the observed and expected frequency of francolins. And what is our next column? Our next column is that this square of the difference between observed and expected frequency is to be divided by expected frequency of that class. So 225 is the square of difference between the observed and expected frequencies of sparrows, and it is divided by the expected frequency of sparrow, and we get 0.4688 value. And then we divide the square of difference between observed and expected frequencies of larks with the expected frequency of larks, and we get 1.7483. And then we divide the square of difference between the observed and expected frequencies of francolins, and we divide that by the expected frequency of francolins, and we get the value, which is 0.3857. Now we take the sum of these values, 0.4688, 1.7483, and 0.3857, and their sum is the value of our chi-square, which is 2.60. So this is our chi-square calculation. The next step is that we have to check that whether this chi-square value is significant or no. So degree of freedom in this case is 2 because there were 3 classes, so 3 minus 1 is 2. The table value that we checked from the chi-square distribution table is 5.991 at probability of 0.05 and degree of freedom 2. So which one is greater, our table value or our calculated value? Our calculated value is less than the tabled value. Therefore, we have to accept the null hypothesis. So probability of null hypothesis to be true is greater than 0.05, which means our results are non-significant. So there is no change in species composition, chi-square 2.62, and probability greater than 0.05. Or we can also say that species composition is same as previously found. The chi-square is 2.6 and the probability is greater than 0.05. So this is the example that how we can use the chi-square goodness of fit test to compare our observed and expected frequencies under some predetermined model or predetermined ratio. So this is the exercise that you have to do at home and share with me the results and discuss with me the results. And if you have any problems in solving this exercise, we will discuss that in the question answer session. So example is the total number of weeds in quadrats collected from different fields. So these are 6 fields, and these are the number of weeds that are found in these fields. So the question is there a significant difference in the weed infestation among different fields? So we have the same observation, we have the same example with different observations, and the question is also saying, is there a significant difference in the weed infestation among different fields? So you have to solve this problem and share the results with me, and you have to follow all the steps, and then you have to come up with a proper result statement in the same format that I have provided you. And this is another exercise. In a dihybrid cross, a progeny of 3,839 seeds was obtained with following categories. So this is another example, and the question is, does the result of this cross follow the Mendel's law of independent assortment? So again, you have to state your hypothesis, you have to choose that what kind of statistical test you are going to use, and then you have to calculate your expected frequencies under your proposed null hypothesis, and then you have to calculate the chi-square value, compare it with the table value, and after you have done your comparison, then you have to state your results in a proper form. So this is all for this lecture, and in the next lecture we will discuss the other type of the chi-square test, which is the chi-square test of independence.